Hey, this is Mrs. Wheatley, and I'm back for Unit 6 video lesson number 10 on changes of state. Now, we've really already talked about freezing and melting, evaporation and condensation, so this time we're really going to focus on sublimation. Now, sublimation occurs in solids with vapor pressures that exceed atmospheric pressure at or near room pressure. And so what happens in sublimation, and opposite of sublimation is deposition, is that you have a solid that goes directly into the gaseous phase and the gas goes directly into the solid phase with missing that liquid phase altogether. So here is an example of sublimation. I like this one because it's pretty cool. Iodine crystals, like when you have a lot of them, they almost look like they're silvery black because they're so dense, they're so compactly packed together. So here we have the molecular form of the solid iodine molecules, and we can see that in the molecular view the particles are really tightly packed together. But if we would heat up this outside test tube, those solid particles, they would start absorbing kinetic energy, and they'd absorb the potential energy first, and then kinetic energy would speed up, and then when their particles are vibrating so much, they're going to escape that surface of the solid particles and go straight into the vapor phase. Now, inside of the big test tube, you have an inner test tube that has liquid water and ice in it, so it's very cold. And so when those vapor molecules, gaseous molecules of iodine, hit that outside of that inner test tube, they immediately go into the solid phase, and you can see the little spiky solid iodine crystals on the outside of that test tube. So I'm just going to kind of skip through these this slide here because it just really goes through what I just explained. Now, sublimation has a lot of useful applications, and one is in the food industry. Solid carbon dioxide, otherwise known as dry ice, is used as a coolant for things like ice cream or frozen food products like pizza when they're being shipped. If you would receive, there's one company called Omaha Steaks, and they send out, meats and frozen vegetables and things like that, and when they arrive in a styrofoam container that's packed in dry ice. Now, the cool thing about the dry ice is that as it absorbs heat, it keeps the materials that it's packed around cool and dry, so they don't get all soggy and everything like it would if it was water ice and it was melting. Okay, so we're going to focus on what are called phase diagrams. And what a phase diagram is, it's a graph that shows the relationship between the solid, liquid, and the vapor states of a substance in a sealed container. And they're usually at atmospheric or standard conditions, like standard temperature and pressure. The phase diagram gives the conditions of the temperature and pressure at which those substances exist in a solid, liquid, and the vapor phase. Here's an example of a phase diagram of water. And so what we see here, it's broken down into the different phases. So this section right here are the conditions in which water will exist as a solid, and this part of the graph here is the conditions in which water exists as a liquid, and here we have the condition in which it exists as a vapor. And so we use this graph to give us information about different things like the changes of state, the normal melting, and the normal boiling point. So each curve represents a single phase of water. Now, this can be pretty much for any substance. Now, in between, so the line that we have right here represents an equilibrium between the liquid phase and the vapor phase at these different temperature and pressures. So this here is the normal boiling point. The normal boiling point would be the boiling point at standard conditions, 101.3 kPa, which is standard pressure, and 100 degrees Celsius. So that's the normal boiling point of liquid water. This is where you would have a dynamic equilibrium between the liquid and the vapor phase. But anywhere along this curve right here, you would have a dynamic equilibrium between the liquid and vapor phase. It just depends on whether you're increasing or decreasing the pressure for water. Okay, now this line right here, okay, represents the equilibrium between the solid and the liquid phase of water, and then the short curve part that you have right here represents the dynamic equilibrium we would find between the solid and the vapor phase. Now you have that point that's circled right there, and that point is called the triple point, and the triple point is the temperature and pressure at which we can find an equilibrium between all three phases of a substance, and in this case is water. So at it looks like at 0.61 kPa and 0.018 I think degrees Celsius, we would see water in all three phases of matter. Now, we can look at the phase diagram and we can predict what would happen if we would lower the pressure of water. So if we decrease the pressure, that's going to lower the boiling point. Let's take a look at that. Here's the normal boiling point. So if we lower the pressure from atmospheric pressure from 101.3, we'll see that, as we lower the pressure, then the boiling point is going to decrease. But when you lower the pressure, then the melting point actually goes up. Okay, so we see this is the melting point right here, 0 degrees Celsius, and as we lower that pressure and we go over to the temperature, we see that the temperature is actually going to lower the melting point. And conversely, we'll see the opposite happen when you increase the pressure. So when we increase the pressure, we go up. We are going to increase the boiling point, but when we increase the pressure, we're going to see that the boiling point is going to go down. And so that is a phase diagram, and in class you're going to get some practice reading and interpreting information on the phase diagram. So for now, I'm going to leave you with be happy and have fun, and this is Mrs. Wheathy. So long for now.